partial order on the symmetric group, which is very closely related to inversions, is called the Bruhat order. So we define the Bruhat order on the symmetric group by saying U is less than W if some reduced expression for W contains a reduced expression for U as a subword. So for example, if we look at the symmetric group in S3, we have the longest word S1, S2, S1, which is also S2, S1, S2. S2, S1 is a subword of that and also of this. S1, S2 is another subword. And then S1 is a subword of each of these. S2 is also a subword of each of these. And then the identity element, which is the empty subword, is a subword of both of those. Let me write this again with one line notation. So the permutation on top is 3, 2, 1. And then we have 2, 3, 1 on the left and 3, 1, 2 on the right. Then 2, 1, 3, 1, 3, 2, and 1, 2, 3 on the bottom. Some easy facts are the identity element is always at the bottom because it's got the empty expression, which is inside of every other expression as a subword. So E is always the unique minimal element. Another fact is that permutations of equal length have to form an anti-chain. None of them can be a sub-expression of the other if they're exactly the same length. So we can see here we've got the zero length element. We've got an anti-chain of the two elements of length 1, another anti-chain of the elements of length 2, and then the one element anti-chain of the one element of length 3. Another easy fact is that the longest permutation, the one with the letters in decreasing order, is the unique maximal element. Another easy fact is that U is less than W if and only if U inverse is less than W inverse. That's because every expression for U turned around is an expression for U inverse, and every expression for W turned around is an expression for W inverse. So if an expression for U is inside an expression for W, we'll turn them around, and that expression backwards is inside the backwards expression for W. Now I won't draw the Bruhat order on S4 on the board, but I'll show it to you here. So this is from a presentation that I gave with Sean Garish and Brian Drake. It's on the syllabus, but there's a link to it so you can have a copy of this for yourself. You can see all 24 elements there. We've got the length 1 elements, the length 2 elements, length 3, 4, 5, and the unique element of length 6 at the top. Now the edges in the Bruhat order are closely related to 2 cycles, or transpositions. That is, if we look at what happens when we go up or go down in the Bruhat order, we're multiplying by a 2 cycles. So here we're swapping the letters in positions 1 and 2. Then we go up here, we're swapping the letters in positions 2 and 3. Then when we go up here, we're swapping the letters in positions 1 and 2 again. If we go up the other side of the hexagon, we're swapping the letters in positions 2 and 3, and then 1 and 2, and then 2 and 3. And then these last 2 edges inside, here we're swapping the letters 2 and 3, which appear in positions 1 and 3. And here we're swapping letters 1 and 2, which also appear in positions 1 and 3. So going up an edge, at least in S3, always corresponds to multiplying by a 2 cycle, also called the transposition. So edges in the Bruhat order are closely related to 2 cycles, also called transpositions. Now there are times when we multiply by a transposition on the left and don't follow an edge. For instance, if we start at the identity element and multiply by the transposition 1, 3, and we switch the letters in positions 1 and 3 and we go all the way up to the top. There isn't an edge there because Hasse diagrams of posets are meant to be transitive. So since 1, 2, 3 is less than 2, 1, 3, which is less than 2, 3, 1, which is less than 3, 2, 1, we don't need another edge telling us that 1, 2, 3 is less than 3, 2, 1. So not every multiplication by a transposition corresponds to an edge, but every edge represents multiplication by a transposition. All right, I want to observe that 2 easy expressions. Here we go. 2 reduced expressions for the transposition A, B, for some indices A and B, are SA, SA plus 1, SB minus 2, SB minus 1, SB minus 2, down to SA plus 1, SA. Now we don't need to go up to SB because that would swap letters in positions B and B plus 1. But we don't want to touch B plus 1. Another expression is SB minus 1, SB minus 2, all the way down to SA and then back up again. So let's write out the letters 1 through N. And see why these reduced expressions make sense. So multiplying by SA first, I'm thinking of applying these from right to left, although these expressions are palindromic, so even if we would apply them from left to right, it wouldn't make a difference. But if we apply from right to left, SA is going to swap the A in the A plus 1, and then SA plus 1 is going to put the A in the next position. So we keep going until A goes all the way up to position B. Our last swap is going to be swap letters in positions B minus 1 and B. And after that, A is going to be there. And then we'll have B in one position earlier and want to get that one back to position A. So that's why we stop at B minus 1, which will swap these two letters, and then go all the way back down to A, so that we end up with B where the A was and A where the B was. Similarly, we could start with the B and move that to the left first, and then move the A to the right second, and that's what the second reduced expression here does. So the two-cycle or transposition AB has at least two palindromic reduced expressions. Now I claim that every element of the symmetric group of the form WSI W inverse is a transposition AB for some indices AB. So we know that conjugacy classes in Sn are sets of permutations that share cycle type. Now the cycle type of Si is 2 and n minus 2 ones, because we've got I and I plus 1 in a cycle together and everything else in its own one cycle. So that means WSI W inverse, which is conjugate to Si in the same conjugacy class, that must also have this cycle type. right, and now to justify what I said about the edges corresponding to multiplication by transposition always, I claim that if u is less than v in the Bruhat order and length of v is exactly 1 greater than length of u, then there is a transposition AB such that AB U equals V. So indeed every edge is multiplication on the left by a cycle. All right, to prove this, since U is less than V, and length of V is length of U plus 1, there's a reduced expression for V, which if we took out exactly one generator, we'd get a reduced expression for U. Because by the definition of Bruhat order, V is greater than U in the Bruhat order only if it contains, if a reduced expression for V contains a reduced expression for U. If the length is 1 greater, that means that there's just one generator we can take out to get a reduced expression for U. So there is a reduced expression for V which is, I'll say, a reduced expression for U with one generator inserted somewhere. So one additional generator inserted somewhere. So that means V looks like SI1 through, let's say, SIL, and let's say Sij is the one that we could remove to get a reduced expression for U. Some people put a hat over what you're removing to mean the same expression as the one above, but with this element removed. Now, if we're clever, we can express U as V with something multiplying it on the left. If we wanted to get rid of the Sij, we could multiply on the left by Si1, and then Si2, and then Si3, etc. up to Sij. That would get rid of all of this. And then we could left multiply by Sij minus 1 to put the Ij minus 1 back, and then Sij minus 2 to put that generator back. And we can put all the generators back except for Sij. So we can multiply by Si1 up to Sij and then, well, let me put the minuses in here. Sij, Sij minus 1 up to Si. So U is this because these two SIs are going to cancel, and then the SI1s are going to cancel, SI2s are going to cancel, everything up to Sij is going to cancel, and then we're going to replace Sij minus 1 through Si1. So that'll be like taking out the Sij. So again, here is V. We're multiplying it by this palindromic expression T, which is a conjugate of Sij, because it's got some permutation here and then its inverse over there. And then, so all of this cancels. And that leaves us with Si1 through Sij minus 1, and then Sij plus 1 through Sil, which is precisely U. So this T has the form W Sij W inverse, and so that has to be of the form AB. That's a 2-cycle. So if U is less than V in the Bruhat order and the length difference is 1, there's a transposition that multiplication by that transposition brings us up the edge. And now I want to claim something of a converse. If ABU equals V and length of V equals length of U plus 1, then there is a reduced expression for U inside of actually every reduced expression for V. All right, so to prove this, let's write any reduced expression for V. Actually, let me start the proof a little bit differently. All right, since the transposition AB times U equals V, and length of U is less than length of V, we have VA being greater than VB. The length of V is greater, so that means that when we swap two letters, we're putting them out of order. So in V, the permutation with greater length, VA is greater than VB. So V looks like something like V1 through VA minus 1, VA plus 1 through VB minus 1, VB plus 1 through VN. And then U, which differs from V only because we swapped the letters in positions A and B, then has U1 equal to V1. So I'll just write V1 up to VA minus 1. Those are all the same. Then we've got a VB here in position A, VA plus 1 up to VB minus 1, and then a VA in position B, and then VB minus 1 through VN are all the same. Right, now let's write any reduced expression for V. We'll write the reduced expression and we'll draw the wiring diagram corresponding to that reduced expression. Alright, since VA is bigger than VB, that means the wire starting at A ends up higher than the wire starting at B. And then there's other crossings in here. All right, now let's cut out the generator. Maybe I put too many X's in here close to the important one. So this is a wiring diagram, so we should have vertical slices, each of which has exactly one X in it. So let's cut out the slice that has that X in it, where the path starting at A and the path starting at B crossed. So we'll cut out the slice corresponding to one generator. Where the paths starting at A and B cross, and replace it with just all horizontal lines. So that's like replacing the generator in the reduced expression with the identity element. So if we do that, then these two paths don't cross anymore. Something like, they do something like that. So the resulting permutation has VA in position B and VB in position A with no other changes. But that's exactly what U is. It's got VB in position A and VA in position B. And further